For decades, early physicists believed that heat was a physical substance. They thought it was a fine, invisible fluid called caloric that naturally flowed out of hot objects and pooled into cold ones. In 1798, Benjamin Thompson, known as Count Rumford, was boring a brass cannon. He observed that the friction from turning the drill generated enough continuous heat to actually boil water. If heat were a fluid trapped inside the metal, it would eventually run out. Instead, the heat kept coming as long as mechanical work continued. This proved that heat is not a substance, it is energy in transit, converted directly from mechanical work into internal molecular motion. But treating heat strictly as an energy transfer creates a new problem. If you apply the exact same amount of thermal energy to two different materials, they do not heat up by the same amount. Look at this comparison. We add identical packets of energy to a mass of water and an identical mass of metal. The temperature of the metals spikes almost instantly. The water barely registers a change. Every material has an inherent resistance to temperature change. To accurately measure how thermal energy moves through the physical world, we have to quantify this resistance, a property known as heat capacity. We define heat capacity, capital S, as the ratio of the total heat supplied to a substance, delta Q, divided by the resulting change in its temperature, delta T. The issue with this raw calculation is that it scales with the physical size of the object. A giant lake will always absorb far more energy to warm up by a single degree than a drop of water. We establish a universal standard by dividing that heat capacity by the material's mass. This gives us specific heat capacity, lowercase s. It tells us the exact number of joules required to heat 1 kilogram of a specific substance by 1 Kelvin. This chart plots the specific heat capacity of water across different temperatures. The required energy isn't a perfectly flat line. It actually dips slightly as the water approaches 40 degrees Celsius before rising again. Physicists and chemists often need to compare materials based on their molecular structure, not their raw weight. To do this, they standardize the measurement by the number of atoms, known as moles. This gives us molar-specific heat capacity. When measured by the mole at room temperature, the energy required to heat elemental solids like aluminum, copper, and silver becomes nearly identical, settling right around a constant value of 3R. Because solids and liquids barely expand when heated, the energy they absorb goes almost entirely into the internal vibration of their molecules. Their specific heat provides a clean, reliable thermodynamic fingerprint. Gases complicate this picture. When heated, a gas expands and pushes against its surroundings, adding a mechanical dimension to the thermal energy equation. To track where the thermal energy actually goes in a gas, we rely on the first law of thermodynamics. This law acts as a strict energy accountant. The first law states that the total heat supplied to a system, delta Q, is equal to the change in its internal energy, delta U, plus the mechanical work done by the system on its environment, P delta V. Consider heating a massive gas locked inside a rigid steel container. Because the container cannot expand, the volume change is zero, meaning zero mechanical work is done. All supplied heat goes directly into raising the gas's internal energy and temperature. Now, place that exact same gas in a cylinder with a movable piston resting on top. As the gas heats up at a constant pressure, it expands and pushes the piston outward. This is the mechanism that powers a steam engine. The gas uses a portion of the incoming heat to perform the physical work of moving the piston. To achieve the exact same temperature rise at a constant pressure, you have to supply more total energy than you would for a constant volume, because you have to pay the added energy cost of mechanical work. This leaves every gas with two distinct specific heats, one measured at constant volume, CV, and a larger one measured at constant pressure, CP. We can calculate the exact cost of that expansion using the ideal gas equation, PV equals RT, which ties pressure, volume, and temperature together. If you take the total energy required to heat the expanding gas, CP, and subtract the energy required to heat the locked box, CV, the remainder is the precise energy spent on mechanical work. That remainder equals R, the universal gas constant. Specific heat capacity maps exactly how the invisible transfer of thermal energy is perfectly balanced by the physical, mechanical work done on the world.